Good morning, everyone. Today we're going to talk about communication in mechatronic systems, focusing on one of the most widely used protocols in the Internet of Things, MQTT. My name is Dr. Retchatin Chancharon from Chulalongkorn University, and in this session I'll walk you through what MQTT is, how it works, and why it has become so important in modern engineering and IoT applications. Let's start with a big picture idea. MQTT stands for Message Queuing Telemetry Transport. It's a protocol designed specifically for devices that need to exchange small amounts of data efficiently, even over low bandwidth or unstable networks. Now, why is MQTT so popular? Let's look at some of its key strengths. Lightweight and efficient, MQTT uses very little data and processing power, so it's perfect for small embedded devices like sensors or microcontrollers. Publish-subscribe architecture. Instead of devices talking directly to each other, they send and receive messages through a broker. This makes the system flexible, scalable, and easy to manage. Reliable message delivery. With multiple quality of service, QoS levels, MQTT can guarantee message delivery even when the network isn't stable. Low power consumption. Devices can disconnect or go to sleep to save energy, then reconnect and pick up where they left off. Retained and will messages. These features let the system keep the last known state of a topic and even send a last message if a device unexpectedly goes offline. Cross-platform compatibility. MQTT can run on almost any platform or programming language, from Arduino to Raspberry Pi to cloud servers. All these advantages make MQTT a powerful and practical choice for building distributed sensor networks, smart controllers, and data dashboards. As you'll see in this course, understanding how MQTT works will help you design and maintain robust, connected mechatronic systems that fully leverage the capabilities of IoT technology. Now let's begin with the foundation. What exactly is MQTT? The name MQTT stands for Message Queuing Telemetry Transport. It's a lightweight publish-subscribe communication protocol that was originally designed for machine-to-machine, or M2M communication, in environments where bandwidth is limited or network connectivity is unreliable. In simple terms, it was built for devices that need to send small packets of information, like sensor readings, efficiently and reliably. Think of applications such as smart agriculture, remote monitoring, or even industrial automation, where devices must keep talking to each other despite weak internet or power constraints. MQTT has now become one of the most widely adopted communication standards for the Internet of Things IoT. It is used everywhere, from home automation systems like smart lights and thermostats to industrial robots, medical sensors, and connected vehicles. The protocol itself operates on top of TCP/IP, which ensures reliable data transfer. However, for even lighter devices or wireless sensor networks, there's a variation called MQTT-SN. The SN stands for sensor network, and that version typically uses UDP instead of TCP. Here's a simple way to remember the difference. MQTT over TCP/IP, reliable, stable, for general IoT systems. MQTT-SN over UDP, faster, lower power, and designed for small embedded devices with simple connections. So to summarize this slide, MQTT gives us a structured, low-cost, and scalable way to send data between devices. It's efficient enough for small microcontrollers, yet powerful enough to support large, distributed IoT networks. Now that we understand what MQTT is and why it's so widely used, let's look at some key terms that form the foundation of how MQTT works. In MQTT, there are 6 main concepts you should remember. 1. Broker or server. Think of the broker as the post office or message hub. It receives all messages from publishers and then delivers them to the appropriate subscribers. The broker doesn't care who the devices are. It only cares about which topic each message belongs to. 2. Publisher. The publisher is the device or program that sends out data. For example, a temperature sensor publishing temperature readings to the broker every few seconds. 3. Subscriber. The subscriber is any device that listens to a topic. For instance, your dashboard or mobile app might subscribe to the topic, home/garden/temperature to receive real-time updates. 4. Topic. A topic is like the address for your messages. It's a string that defines where the message goes, such as home/garden/fountain. MQTT also supports wildcards, the plus and hash symbols, to make subscriptions more flexible. For example, subscribing to home/plus/temperature lets you listen to temperature data from all rooms in a house. 5. Message or payload. This is the content of the communication, the actual data being sent. It could be a simple string like turn it on, or a structured JSON file with sensor values. 6. Quality of service, QoS. QoS defines how reliable the message delivery should be. It can be set to 0, 1, or 2, meaning at most once, at least once, or exactly once. We'll look at this more closely in the upcoming slides. One more thing to note, MQTT usually runs on port 1883 by default, and each client has its own unique identity or client ID. This ensures the broker can keep track of who's connected and manage messages properly. So in summary, MQTT communication revolves around 3 roles: publisher, broker, and subscriber, all connected through a structured topic system. Once you understand these 6 core elements, the entire MQTT ecosystem becomes much easier to design and troubleshoot. Now that we know the main components of MQTT, the broker, publishers, and subscribers, let's talk about some important features that make MQTT such a powerful and reliable communication protocol. These features are what make MQTT stand out, especially when compared with heavier protocols like HTTP or WSS. Let's go through them one by one. 1. Clean session versus persistent session. When a client connects to a broker, it can choose whether it wants to keep its connection data. A clean session means that every time the client reconnects, it starts fresh. No previous subscriptions or messages are remembered. A persistent session, on the other hand, tells the broker to store all the subscription information and queued messages, even if the device temporarily goes offline. This is very useful for IoT devices that disconnect often. 2. Retain messages. A retained message is one that the broker keeps in memory even after it has been delivered. When a new subscriber joins later, it will immediately receive the last retained message for that topic. For example, if your sensor last reported 28 degrees Celsius, any new subscriber will instantly see that value without waiting for the next update. 3. Last Will and Testament, LWT. This feature might sound dramatic, but it's incredibly practical. The last will and testament allows a device to define a message that will be sent automatically if it disconnects unexpectedly. For instance, if a device loses power or network connection, the broker can publish a message like "device offline" to alert other clients. This helps the system handle failures gracefully. 4. Keep alive messages. The Keep Alive feature ensures that the broker knows whether a client is still active. The client sends a small ping message at regular intervals to say, "I'm still here." If the broker doesn't receive a ping within the expected time, it assumes the client has dropped out and triggers the LWT message if one is set. Together, these features make MQTT not only lightweight but also robust, capable of handling unstable networks, intermittent connections, and devices that go offline and come back online. So in short, MQTT is more than just a simple data passing protocol. It's a smart and reliable system designed for real-world IoT conditions, where connectivity can't always be guaranteed. In the next slide, we'll see how all these features come together to form a complete MQTT communication cycle. All right, now let's connect what we've learned about MQTT to something hands-on. As you know, the Raspberry Pi is a small but powerful microcomputer. It can run a full operating system, connect to the internet, and interface directly with sensors and actuators. One of its biggest strengths is that it allows us to handle IoT data very easily through an abstract communication layer, and that's exactly where the MQTT protocol comes in. The easiest way to test or visualize MQTT communication on a Raspberry Pi is by using Node-RED, which conveniently comes pre-installed with the Raspbian OS. Node-RED is a graphical, flow-based programming tool. Instead of writing long lines of code, you can simply drag and drop nodes, connect them with virtual wires, and configure a few basic parameters. This is one of the best things about the Raspberry Pi platform. You can combine hardware control using Python or C++ with high-level IoT logic using Node-RED, all on the same device. In today's lecture, we'll use Node-RED to test sending and receiving MQTT data between devices. Let's walk through the process step by step. 1. Connecting to the broker. In Node-RED, drag an MQTT input or MQTT output node into your workspace. Then configure it with your broker information. For example, our test broker uses the address 161.200.84.240 and port 1883. This tells Node-RED where to send or receive data. 2. Publishing data. The MQTT output node is used to send messages. For example, a sensor like the ESP32 can publish data such as temperature or humidity to a topic like home/garden/temperature. In Node-RED, we can simulate this using an inject node. Simply press the button, and the data will be published to the broker immediately. 3. Subscribing to a topic. To receive messages, use an MQTT input node and subscribe to the same topic. Any message published to that topic, whether from Node-RED, your ESP32, or another device, will appear in your flow. You can connect it to a debug node to view live messages, or to a dashboard node to visualize data in real time. 4. Testing the flow. Once you deploy the flow, you'll see messages being sent and received instantly. This is the publish-subscribe mechanism in action. Exactly what we studied earlier, but now happening live on your screen. Node-RED also supports features like different QoS levels, retained messages, and even the last will and testament, so you can explore all the reliability options of MQTT without writing code from scratch. So to summarize, Node-RED on Raspberry Pi gives us a visual, hands-on environment to experiment with MQTT communication, bridging between physical hardware and the digital data layer. In the next part, we'll take this concept further by connecting real sensors and actuators and displaying live data on a custom dashboard interface for monitoring and control. Now that we've successfully sent and received data through MQTT, the next logical step is to visualize that data. And for this, we use what's called a dashboard. A dashboard is a graphical interface that allows us to monitor, analyze, and control IoT systems in real time. It's not specific to Node-RED. In fact, dashboards can be built using many different platforms, such as Grafana, Thingsboard, MQTT Dash, or even custom web applications. The purpose of a dashboard is simple. It helps us transform raw sensor data into meaningful information that can be seen and understood instantly. Let's look at the basic concepts behind how dashboards work. 1. Building the dashboard. A dashboard typically consists of visual components, for example, gauges, charts, indicators, text panels, and switches. These components represent live data from your IoT devices. For instance, a temperature sensor value can appear on a gauge, while a humidity sensor can be plotted as a line chart over time. 2. Connecting data. The dashboard receives input from your data source, in our case from the MQTT broker. Each widget subscribes to a topic, and when new data arrives, the dashboard updates automatically. This allows you to see changes in real time as sensors publish new values. 3. Understanding meaning and trends. This is where data visualization becomes valuable. By observing your dashboard, you can begin to identify patterns and relationships. For example, how temperature changes throughout the day, how humidity responds after irrigation, or how light intensity might correlate with plant growth. These insights help engineers move from just collecting data to understanding system behavior, which is the true goal of IoT analytics. 4. Correlation and control. A dashboard isn't just for observation. It can also be interactive. You can design controls that send commands back through MQTT to your devices. For instance, if the temperature exceeds a set threshold, the system could automatically trigger a fan or valve to respond. In short, a dashboard turns your IoT system from a data pipeline into an intelligent, user-facing control platform. It enables both real-time monitoring and feedback control, bridging the gap between raw sensor data and actionable engineering decisions. In the upcoming section, we'll explore how message reliability, especially the concept of quality of service, QoS in MQTT, ensures that every piece of data shown on the dashboard is accurate and dependable. All right, let's take a look at this diagram. It shows a complete MQTT communication network in action. In the center, you can see the MQTT broker, which acts as the message hub of the entire system. Every message goes through the broker. It receives messages from publishers and then distributes them to all subscribers who are interested in that topic. On the left, we have a Raspberry Pi, which in this example functions as the publisher. It reads data from a rotation sensor, such as the angular speed of a motor or shaft, and publishes that data to the topic sensor/rotation. The Raspberry Pi sends this message to the MQTT broker, typically running on a server, a cloud service, or even locally on another Raspberry Pi. Now, on the right side of the diagram, we have two subscribers. The first one, at the top, is a computer running MATLAB. This client subscribes to the same topic, sensor/rotation, allowing MATLAB to receive live sensor data in real time. From there, we can visualize the data, run analysis, or control other devices based on those readings. The second subscriber, at the bottom, is an Arduino board. It also subscribes to sensor/rotation, meaning it will receive the same published data. The Arduino might use that data to perform an action, for example, adjusting a motor speed, turning on a light, or activating a safety alert. Meanwhile, the broker can also store all incoming data into a database, shown here at the bottom of the diagram. This allows us to record sensor readings for long-term monitoring, analytics, or digital twin applications. What's important here is that the publisher, the Raspberry Pi, doesn't need to know who the subscribers are. It just sends data to a topic. The broker takes care of routing messages to everyone who has subscribed to that topic. This design is what makes MQTT so flexible and scalable. You can have one publisher and hundreds of subscribers, or the other way around, all communicating asynchronously. So to summarize, the Raspberry Pi acts as the publisher, sending sensor data. The MQTT broker handles message distribution. The MATLAB client and Arduino board act as subscribers, receiving and using that data. And finally, the database logs everything for future processing. This architecture, the publish-subscribe model, is the foundation of most modern IoT systems. It enables real-time, reliable, and decoupled communication among smart devices across your entire mechatronic network. Let's take a look at this simple but very powerful diagram. It shows the core concept of MQTT communication in a real-world IoT context. As we've discussed earlier, MQTT stands for Message Queuing Telemetry Transport. It's a lightweight machine-to-machine or Internet of Things IoT communication protocol designed for devices that send small pieces of data efficiently and reliably, even when the network connection is weak. In this diagram, the process starts on the left with the temperature sensor. The sensor continuously measures the temperature, for example, 21.3 degrees Celsius, and then publishes that reading to a specific MQTT topic. The data is sent to the MQTT broker, shown here in the center. The broker acts like a post office or message hub. It doesn't analyze or modify the data. It simply makes sure that the right devices receive the right messages. On the right-hand side, we have two subscribing devices. In this case, a desktop computer and a laptop. Both are subscribed to the same topic, so when the sensor publishes the temperature value, the broker automatically delivers the same 21.3 degrees Celsius message to both devices. Notice that the publisher, the sensor, doesn't need to know who the subscribers are, or even how many of them exist. It just sends its data to the broker, and the broker handles everything else. This is the key strength of the publish-subscribe architecture. It's asynchronous. Publishers and subscribers don't need to be online at the same time. It's scalable. You can add more devices without changing your main program. And it's lightweight. using very little bandwidth and power. So to summarize, the sensor machine publishes data. The broker acts as the middleman. The devices, machines, subscribe to receive that data. This is what we call machine-to-machine, M2M communication, a sensor talking to other machines automatically without human intervention. MQTT makes this possible with just a few lines of code and minimal network load, which is why it has become the standard protocol for IoT systems in smart homes, factories, and research labs alike. Now that we've seen how Node-RED can visualize and interact with our MQTT data, let's take a closer look at one of the most important aspects of MQTT communication, quality of service, or QoS. QoS defines how reliable the message delivery is between the publisher and the subscriber. In other words, it determines how sure we are that a message actually arrives at its destination. MQTT defines 3 levels of QoS, and understanding these will help you choose the right balance between speed, reliability, and network overhead in your IoT system. Let's go through them one by one. 1. QoS 0, at most once. This is the simplest and fastest mode. The publisher sends a message only once and doesn't check whether the subscriber receives it. It's a fire and forget method. No acknowledgement, no retry. We usually use QoS 0 when the data isn't critical. For example, frequent sensor readings that are updated every few seconds. If one packet is lost, it's not a big deal because a new one will arrive soon. 2. QoS 1. At least once. This mode ensures that the message will arrive, but it might arrive more than once. The publisher waits for an acknowledgement called back from the broker. If it doesn't receive it, it will resend the message. This level is suitable for cases where losing a message is unacceptable, but receiving a duplicate message is fine. For example, turning on a pump or updating a dashboard value. 3. QoS 2. Exactly once. This is the most reliable level and also the most complex. It uses a 4-step handshake between the publisher and the broker. Publish, pubrec, pubrel, and pubcomp, to make absolutely sure that each message is received once and only once. This mode is important in systems where duplication could cause errors. For example, in financial transactions, inventory updates, or critical control commands. However, QoS 2 adds more network traffic and latency, so we usually use it only where necessary. So to summarize, QoS 0, fastest, least reliable, good for frequent updates. QoS 1, reliable delivery, possible duplicates, good for general IoT data. QoS 2, guaranteed once-only delivery, best for critical operations. MQTT's ability to choose between these levels is what makes it so flexible for different kinds of IoT and mechatronic applications. In the next slide, we'll visualize how these QoS mechanisms actually look in a real message flow, so you can see how the broker and clients interact during each level of reliability. Let's move on to Node-RED, where we can actually set up, connect, and manage MQTT communication visually. Node-RED provides 2 key node types for MQTT: the MQTT input node, which subscribes to topics, and the MQTT output node, which publishes messages. These 2 nodes form the core of any MQTT flow inside Node-RED. So let's open one of them and take a look at the configuration window together. 1. Broker settings. The first thing we need to do is define our MQTT broker. This is the central server that routes messages between all publishers and subscribers. In our example, the broker is at 161.200.84.240 using port 1883, which is the standard MQTT port. In Node-RED, you can create a connection profile and give it a clear name, something like 5G server or local broker, to help you identify it later. Then you'll configure several connection options such as client ID, a unique name for your Node-RED instance. Keep a live interval. How often Node-RED pings the broker to confirm the connection, usually around 60 seconds. Connection timeout. How long Node-RED waits before deciding the connection is lost. Clean session. Whether the session should start fresh each time or keep previous subscriptions and queued messages. You can also add extra parameters such as username and password, enable TLS/SSL encryption for secure connections, or define a last will and testament (LWT) message. This is a message that the broker will send automatically if Node-RED disconnects unexpectedly. 2. Topic configuration. After setting up the broker, the next step is to define your topic. This is the address that your data will use. For example, home/room1/switch1/power for a smart home light or switch. Sensor/lab1/temperature for a lab temperature sensor. You can also choose the quality of service, EQS level, 0, 1, or 2, depending on how reliable you need message delivery to be. And you can enable the retain option if you want the broker to keep the most recent message for new subscribers. 3. Node naming and flow structure. To keep your flow organized, it's good practice to give each MQTT node a clear name. For example, room 1 temperature, output, or MQTT to databoom. You can then connect these nodes with other elements like inject, function, and debug nodes to build a complete workflow. From generating sensor data, to sending messages, to logging or visualizing the results. 4. Testing the connection. Once everything is configured, click Deploy. Node-RED will connect to your broker, and you should see a small green status indicator below each MQTT node. That means the connection is active and messages are flowing. You can test this by publishing a simple message. For instance, sending a string like "Hello MQTT," or by watching live data appear in the Debug tab or on your dashboard. 5. Advanced options. Node-RED also gives you control over more advanced features, like clearing publish history, setting automatic reconnections, or handling multiple in-flight messages. These are especially useful when you start scaling up your IoT system or working with multiple brokers. So to summarize, Node-RED gives you full visual control of MQTT communication. You can define your broker, choose topics, adjust QoS levels, and design the entire message flow, all through an intuitive drag-and-drop interface. In the next part, we'll extend this setup by adding dashboards, control panels, and feedback loops, turning your MQTT network into a truly interactive smart system. Now that we've covered the basic concepts of MQTT, the broker, publisher, and subscriber, let's look at some software tools that we can use to test and visualize MQTT communication in action. MQTT is an open standard, which means there are many freely available tools that allow you to publish and subscribe to topics without writing a single line of code. These tools are perfect for learning, debugging, or demonstrating how messages move through an MQTT network. One of the most popular examples is MQTT-FX, which you can download from https://mqttfx.jensd.de. MQTT-FX is a desktop MQTT client available for Windows, macOS, and Linux. It provides a clean, easy-to-use interface that lets you connect to a broker by simply entering the server address and port, for example, 161.20, 0.84.240 on port 1883. Publish messages to a topic such as home/garden/temperature. Subscribe to multiple topics at once to monitor data from several devices in real time. You can actually see the entire publish-subscribe process happen instantly. When one device sends data, the other clients display the message almost immediately. That makes MQTT-FX an excellent tool for learning and demonstrations. If you're using Windows, you might also want to try MQTT Explorer or MQTT Box. MQTT Explorer provides a powerful tree view interface that lets you browse all topics, view retained messages, and even chart live data. MQTT Box is another versatile option that works across platforms. It's great for testing multiple brokers or comparing payloads quickly. For mobile devices, there are several excellent MQTT clients as well. MQTT- for Android, ideal for building quick dashboards with switches, sliders, and charts. IoT MQTT panel and My MQTT, which allow you to monitor and control devices right from your smartphone. These tools are extremely useful for both students and engineers because they allow you to experiment with MQTT visually before diving into code. So before we move on to Node-RED or Python programming, I highly recommend that you try MQTT-FX or MQTT Explorer first. They'll help you understand exactly how messages are published, delivered, and subscribed, step by step, in a live IoT environment. In the next slide, we'll take this a step further by integrating these tools with real hardware, such as a sensor node or microcontroller, so we can observe how the data flows through the broker in real time. Before we end this lecture, I'd like to briefly introduce another important IoT communication protocol, the REST API. We won't go into the full technical details of this protocol in this clip, but it's important to be aware that there are other powerful and effective communication standards besides MQTT. REST, or Representational State Transfer, is an architectural style used for web-based communication between machines. It operates over the standard HTTP protocol, the same one your web browser uses, allowing different applications to send and receive data easily across the internet. In a RESTful system, data is organized as resources, and each resource is identified by a unique URL. Clients interact with these resources using common HTTP methods such as get on to read or retrieve data post, to create new data put, to update existing data delete, to remove data. For example, your program might send a GET request to https://api.weather.com/temperature to receive real-time weather information in JSON format. REST APIs are very common in both web and IoT applications because they are simple, platform-independent, and easy to integrate with cloud servers, mobile apps, and databases. However, and this is important, REST works on a client-server model, meaning the client must actively request data each time it wants an update. This makes REST excellent for on-demand communication, but less efficient for continuous, real-time data exchange. In contrast, MQTT is event-driven and lightweight, allowing devices to automatically push updates to subscribers as soon as new data is available. So to summarize, REST API is best suited for cloud integration and web-based applications. MQTT is best suited for real-time, continuous IoT communication between devices. Together, these two protocols form the foundation of modern IoT systems, REST for cloud and API-level integration, and MQTT for fast, efficient, and real-time device communication. And that brings us to the end of this lecture. In our next session, we'll see how to connect these communication protocols with real hardware to create a complete interactive IoT system. And that brings us to the end of today's lecture on MQTT communication and data visualization. I hope this session helped you understand how devices exchange data using the publish-subscribe model, how brokers, publishers, and subscribers work together, and how we can visualize that information through dashboards and control interfaces. Remember, MQTT is one of the key building blocks in modern IoT and mechatronic systems. It's lightweight, efficient, and designed exactly for the kinds of smart, connected devices we work with in engineering today. Thank you all for your attention and participation. If you're watching this as part of our course series, don't forget to review your notes, try out the example MQTT tools like MQTT-FX or MQTT Explorer, and experiment with creating your own data flow between devices. Once again, I'm Dr. Ratchatan Chancharoen from Chulalongkorn University, and thank you very much for watching. See you in the next lecture.